Today we're going to be taking a look at this low voltage LED light bulb. We'll actually go ahead and start by looking at the packaging and seeing what it claims. So it's a 10 watt A19 LED light bulb, 1000 lumens, 25,000 hours, AC or DC, 12 to 24 volts. And then there's the lighting facts page on this side, which doesn't really tell you a whole lot. 1000 lumens gives you the estimated energy cost and the color temperature, which is not checked off. You can see on the back, though, these are 4,000 Kelvin. It says non-flickering, shows you all the things you can put it in. Non-dimmable, CRI of 82 plus, which is good. And then there's some specifications here, which are mostly just how long it lasts. Has a 2-year warranty, apparently. 10 watts, the size. The one obvious warning that I have to make about this is that it is a 12 to 24 volt DC bulb with a standard Edison screw base, so there's not really anything stopping you from physically screwing this into the lamp that I just pulled this bulb out of, which is a 120 volt lamp. So you would not want to screw this into a normal mains voltage thing. Now, I actually bought this to replace the old Harbor Fright CFLs, if anyone remembers those, the ones that came in their 45 watt solar kits back in the day. I'm not even sure they still sell those particular bulbs, but those are 4 watt CFLs, and this is a 10 watt LED, so this should be a significant brightness upgrade. You can see this one's 4,000 Kelvin. They had a couple different color temperature options. I think there was a 3,000, a 4,000, a 5,000. I went with 4,000 because this is going out in a shed, so a little bit more industrial looking light I think is okay. These bulbs were fairly cheap. They work out to $2.43 per bulb, but it was a Black Friday special, so take that pricing with a little bit of a grain of salt. Let's go ahead and turn it on and see what happens. So instead of buying a lamp holder like a sane person, I went ahead and 3D printed one. Wouldn't recommend using something like this for a 120 volt bulb, but for this, it's just fine. It's going into a current limited power supply, so I'm not at all concerned about that. There we go. It lights up, much like a light bulb, and it is currently pulling 650 milliamps at 12.6 volts, but that current is dropping off slowly. It's taking about 8.1 watts right now, but that's dropping slowly as it warms up. I've left this bulb on for a while now. It has gotten quite toasty, especially the base down here. These are very light, by the way. I don't know if I mentioned the weight of these or not, but it doesn't feel like there's a whole lot in them. We have settled down to 7.8 watts, it looks like, which is a fair bit under the claimed 10 watts, which is a little bit unfortunate. But let's go ahead and do some brightness testing. So I'll stick this right about here. I've got to just gonna kind of prop it up on this desk light if I can. All right, so I've just got that bulb sort of dangling off the front of my desk lamp, and I'm going to arrange some objects just to give you an idea of color rendering accuracy. It does claim to have a CRI of 82 plus. If you're unfamiliar with CRI, that stands for Color Rendering Index, and it's a percentage based off of pure sunlight. So a CRI of 100 would be equivalent to sunlight. Modern LEDs can get well into the 90s. These are claiming a CRI of 82, which I think is going to be pretty good. Certainly much better than a traditional CFL, but it's probably not going to be as great as the halogen bulb that's in this desk lamp. So we'll see if we can get some idea here. So let's go ahead and turn off the studio lighting. I'm not entirely sure what the CRI of these lights is, but it's quite high. You know, it really doesn't look too bad at all. It's casting shadows differently, of course, because the studio lights are behind me. The light bulb right now is in front of me. But the greens and the yellows look quite good. The purple here, blue on the hot glue gun. Of course, blue is going to look decent. The base LEDs will undoubtedly be blue, and then it'll have a phosphor over it that converts that blue into a bunch of other colors to make visible white light. So I think the color rendering on these is good enough. So let's go ahead and turn on the halogen bulb, which is a different color temperature, so it's probably going to look different. Yeah, there you go. There's the halogen bulb. It's got a warmer glow. The halogen bulb will be like a 2700 Kelvin. And of course the colors look just fine on that bulb. It does seem to be a bit dimmer compared to our LED friend. The halogen bulb in that lamp is a 60 watt equivalent. This light bulb should be a 100 watt equivalent. So there we go, turning the LED back on, it kind of completely swamps everything out. So this is the power supply I'm using to power the light bulb, and you can see we're sitting pretty steady at about 7.8 watts. What I want to see is what happens if we start upping the voltage here, because this bulb is designed to run from anything from 12 to 24 volts, AC or DC. You can see our power draw, now that we're set to 24 volts, is still 7.8 watts, and our current draw has been cut in half. So this will be using some kind of a buck regulator inside of it, which makes this $2.43 light bulb more technologically advanced than that quite expensive Milwaukee M12 tool that we looked at a while back on the channel. So my next question is what voltage does it start to lose power at? So if you were powering this off of some kind of a 12-volt battery system, it's not unreasonable for it to be running at less than 12 volts. So I don't know where it cuts out at. So we're down to about 10.5, and it's actually starting to draw. Well, it was drawing more power there for a second. You see around 10.7 volts, it actually goes up some. 10.5 is about as low as you're going to run a 12-volt battery system, so I think it's doing quite well. And then, yeah, 10.4, we're starting to lose some power. Well, it's holding in there. 7 watts, still pretty bright. Now I'm starting to notice it dim every time I turn the knob down there. Down to 4 watts at 9.6 volts. And we're down to 2 watts at 9 volts, so just barely any light coming out of it. .05 watts at 8 volts, and it is just barely glowing ever so slightly. So if you use a constant voltage DC source that you can adjust up and down, you can actually dim it within a very small range. Let's go ahead and crack this open and see what it looks like on the inside. One thing I will say I immediately don't really like about these is that the build quality is not the greatest. So when I went to install this into that light socket that you saw earlier, I was twisting it by the front of the bulb because that's kind of the natural thing to do. And well, it kind of just pops right apart. There is some glue on this globe, but it's not doing a whole lot to stop that from coming apart. Doesn't really matter, as you can see, it just kind of pops right back in. It's a nice little snap fit. I don't think these are rated to be waterproof or anything crazy like that, so it's not the biggest deal. If this was a 120 volt light, I wouldn't like it because that would mean that you just exposed 120 volt stuff, but because it's 12 volts, it's not such a big deal. Like if you touch some of this, the worst case, you get a little tingle probably. You're not going to get electrocuted or anything by something like this. All right, now we've got her focused. You can see there's a model number in there. 24 volt, whole bunch of other stuff, AC, DC, 12 volt, EMC, whatever that means. So looking at this guy, there's really not a whole lot here. We've got a couple of what look to just be power connectors, this guy and this guy. So those must just be running down to the contacts. I don't think there's anything under this board. And then looking on the rest of it, we've got 4 diodes, which are undoubtedly in a bridge rectifier, so this thing can run on AC. There's this little guy marked as L1, which appears to have an option to put a much larger inductor in its place. Not really sure what the deal with that is. Maybe they figured out they can get away with a smaller one, so they just kind of hand solder that guy in there, it looks like. But it seems to work. You got another bigger inductor. This one is likely the one that's being used for the switch mode power supply that's inside this. If I had to guess, this other one is probably to reduce conducted emissions. So basically just a power supply filter so the noise from this buck converter doesn't get onto the wires that are coming out of this device. Flipping around here, you can see the device that's making this tick. And there's a couple of resistors, so that one looks like it's 5.6 ohms and the other one is 130 ohms. Those are likely to set currents on this device. We'll see if we can't find a data sheet for this thing and see exactly what makes that work. But other than that, there's a capacitor here, and we have 2, 4, 6, 8, 10 LEDs. And interestingly enough, it would appear as though that there are spots for 5 more LEDs that are not populated on this guy. You can actually see by looking at the traces that all of those LEDs are just in parallel. You can see the coming straight off the leg of this inductor, there's a big ring of copper all the way around. And then this other side, the inner ring on the LEDs, goes all the way around back over to here where these resistors are, it looks like, and then continues going all the way back around. I am a little bit curious on what the forward voltage of these LEDs happens to be. We'll see if we can't probe that. More specifically, we'll see if we can't probe that without getting blinded by it. You go ahead and try to fire this thing up at 8 volts. Yeah, there we go. You can see that the LEDs are just barely glowing in there. I'm mainly just curious if the voltage across these LEDs is something like 3 volts or if these have multiple LED chips inside of them. Should actually just be able to measure across these two pads. Oh, there you go, 7.515 volts. So the voltage across these individual LEDs is higher than what you'd think, which means that they probably have multiple LED chips within one package, which is kind of neat. Let's see if we can't figure out what voltage they actually run at with some current going through them. Try not to look at it, and we'll crank her up here. So that's with the prescribed amount of voltage, 8.841 volts, and slowly dropping. So right around 9 volts, which would kind of imply that there are 3 LED chips in series in each of these individual, quote-unquote, individual LEDs. I am curious if we can turn the voltage down enough to where we can see individual LEDs in here. Oh, yeah, we sure can. There you go, that's at 7.6 volts. You can actually see the 3 series LEDs, which is pretty neat. Our little voltage sensing experiment here has also uncovered probably a small little mystery. This IC is likely putting out a constant current, and you saw that as these LEDs heated up, the voltage was dropping, which means that the total power of this circuit was also dropping. So that's why we're seeing the power being supplied to the entire thing drop over time. That is expected for something that's outputting a constant current driving LEDs, because LEDs have a negative temperature coefficient, which means that the forward voltage across the LED will drop as it heats up. So I've done a bit of research here. We're going to talk about some of the components inside this light. First off, the main driver chip is the MT7201, which is this guy. 1 amp LED driver with an internal switch, which that just means that it doesn't need an external MOSFET to run. So a little bit of the description: continuous mode inductive step-down converter. It's really just a constant current buck converter effectively. You can see the maximum output current is 1 amp with an input supply voltage of 7 to 40 volts. It has some different features. I'll touch on a couple of them. Mostly the adjustment pin here. That's kind of interesting. I'll talk about that a little bit. But you can see the typical application circuit. There's a current sense resistor, and at 0.1 ohms, that gives you the full 1 amp output. you can use a higher resistance to lower the output current. Otherwise, fairly typical schematic for something like a buck converter. You've got your inductor, diode, decoupling cap, fairly standard. And then there's this adjust pin, which is not connected in this design and is also not going to be connected in our case because the bulbs that we have do not support any kind of dimming. Scrolling down a little bit further, you can see the absolute maximum ratings for a few things. So input voltage, negative 0.3 up to 40 volts. Current sense voltage is kind of just the maximum ratings for the different pins. I'll scroll down here so you can see what those pins are. The main thing that's interesting to me is the adjust pin. You can either give this a PWM input or you can give it a DC voltage between 3 volts and 2.5 volts, and that will allow you to adjust the output current. Normal operation, you just leave this floating, which is what this bulb would be doing, but the chip allows you to dim the LEDs, which is kind of interesting. The other thing that I would like to do is show you how much current this thing is putting into the LEDs. In that picture I had up a second ago, you see there are 2 resistors here. These are the current sense resistors. One of them is, so the way this works, the R is effectively the decimal point. So if you replace that R with a decimal point, that resistor is 0.130 ohms, and this resistor, which is in parallel with the 0.13 ohm resistor, is a 5.6 ohm resistor. If we do some scrolling in the datasheet, there's a bunch of different graphs. One of them is an efficiency at a 47 microhenry inductor, which is what we have. This is probably assuming full 1 amp of output current, but you see here 3 LEDs in series, which is what we have. At 12 volts, we're around 91, 92% efficient, and up at 25 volts, we're around 88 or so percent efficient, so decent efficiency. We keep digging, we'll eventually find this. Okay, so this formula is what I was looking for. 0.1 divided by RS for values greater than 0.1, because 0.1 is the minimum. That gives you 1 amp of output current. This formula gives you the output current of the buck converter. You can see there's a few examples here. So 0.1 ohms is the full 1 amp. 0.13 ohms is 760 milliamps, and 0.15 ohms is 667 milliamps. We have something a little bit weird. We have a 0.13 ohm resistor in parallel with a 5.6 ohm resistor. So that gives us a resistance of 0.127 ohms, which is very, very close to the 0.13 ohm resistor that they already had in there. So they were really trying to fine-tune this, which I find interesting. We'll go ahead and throw that number into the calculator memory, clear that out, and if you remember, our formula over here was 0.1 divided by the sense resistor. So let's take 0.1, divide that by the sense resistor. That gives us an output current of 787 milliamps. Sorry for the abrupt transition, but I did want to find some equivalent LEDs to what they're using in this light. So we just calculated that they're pushing about 780 milliamps out to all 10 of those LEDs. So that gives us 78, well, let's just call it 80 milliamps per LED. I've fired up DigiKey here. I have 2 filters applied, one being the forward voltage. I'm filtering between 8.5 and 9.5 volts, I believe. Somewhere in that, we measured about 8.8 or 9 volts, I believe it was. I've also applied a physical package size. These LEDs have turned out to be it's a 2835 metric package, or an 1113 in the imperial units. Pretty standard size. You see, even filtering to this, we have 500 and some results. So let's just go ahead and take a look at the basic ratings on the first one. And really what I want to find out here is whether or not it's plausible that these LEDs are being driven safely, let's say. A lot of these cheap LED bulbs will hammer the LEDs, and they don't end up lasting very long if they're doing that. Going over the basic specs here on DigiKey, you can see their test currents are at 100 milliamps, 9.2 volts forward voltage, 80 for the color rendering index, and the absolute maximum current is actually 120 milliamps. So this very well could be the LED that they're using, but the main thing I want to point out here is that if you start looking at test currents, pretty much all of these LEDs are right around 100 milliamps. All right, here we go. Test current, these are at 60. Still don't know what their max current is. Okay, so these ones do have a max of 70. We found some that are lower, so they do exist, which really that just means that it's inconclusive whether or not these are rated for 100 milliamps or not. You know, the unfortunate thing about the LEDs is that we don't have a part number of them, so we really don't know what they are. We can speculate. I'm going to go ahead and give them the benefit of the doubt here and assume that they're either using LEDs that are rated for 100 milliamps or they're using LEDs that are rated for 80, and they're trying to run them at exactly 80 or as close as they can. It is kind of odd to me that they used that extra resistor on there to bring the current up just a few milliamps, really. In conclusion, I like the design of it. I think they're okay, but it's not actually a 10 watt LED. It's an 8 watt LED that's masquerading as a 10 watt LED. I'm not entirely sure why they decided to design them like this, because they probably could have made this a 10 watt LED. Unless 10 watts, the heat dissipation just ends up being too high. That's entirely possible. Even then, they could have marketed the thing as an 8 watt LED instead of a 10 watt, and it would have been more honest. So, you know, for the price, I think these are okay. I think they'll last a while, and they'll do their job. It is just a little bit disappointing that they don't output the full 10 watts. So anyway, that's it for this video. I'll see you next one, guys. Bye.